Assalamualaikum. So now we will go into lesson 4, which is chapter 3. So there is 9 parts to chapter 3, but this video will discuss 5 parts of chapter 3. So the first part of chapter 3, we will talk about electric conduction. And the first learning outcome would be, you should be able to describe microscopic model of current. Okay, that means how the current is transferred or how the current travels. Okay, but before that, we know for the current to travel, it needs to go through a conductor or a metal wire. So a metal wire or a conductor. So here we have an image of a metal wire or a conductor which is not connected to a battery. Okay, and we have metal atoms and free electrons. Okay, so a metal is a solid with valence electrons that are not tightly bound. Okay, electrons are not tightly bound. Instead, they are easily able to move. So these electrons can move. However, when the metal wire or the conductor is not connected to a battery, the electrons are moving freely in different directions. Okay, the electrons are moving freely in different directions. We go to the next slide. Okay, so this is the same one. A metal wire or a conductor contains many free electrons and move randomly in all directions. So these electrons move randomly in all directions when the metal wire is not connected to a battery. Okay, but when the metal wire is connected to a terminal of a battery, okay, when we take the metal wire and we connect it to a terminal of a battery, the potential difference between the battery sets up an electric field. Okay, so when we connect it to the battery, there will be an electric field produced. This electric field is directed from the positive towards the negative terminal. So when we have the battery, so we have the positive and the negative terminal. So the electric field would go from the positive to the negative terminal. Okay, the electric field is directed from the positive towards the negative terminal. And the electric field exerts electric force on the freely moving electrons. So since if there's electric field produced, there is an electric force towards the electrons which are moving freely earlier. So now the electrons cannot move freely anymore. Instead, the electrons are attracted to the positive terminal. Okay, so if we have electrons, so if we, for example, we have electrons here or here, so these electrons would be attracted to the positive terminal which is here. So this is the positive terminal. So the electrons will be attracted to the positive terminal. So they are not moving freely anymore, but they are all moving in one direction towards the positive terminal. Electrons are forced to drift. Okay, electrons are drift one direction, which is the opposite direction of the electric field. So just now the electric field is moving from the positive terminal to the negative terminal, but instead the electron is moving from the negative terminal towards the positive terminal. Okay, the electrons are attracted towards the positive terminal, so the electrons are moving in the opposite direction of the electric field. Okay, so that's how current is transferred. And this is the model, microscopic model of the current, which is called, so we give them a term which is called a drift velocity. So when we say drift velocity, it refers to the velocity of the electron traveling towards the positive terminal. This only happens when the battery is applied. When there's no battery, the electrons are moving freely. Okay. So to summarize, the direction of current flow. So direction of current flow would be in the same direction as the electric field. Okay, direction of current flow would be same direction of electric field, which is from the positive terminal to the negative terminal. Okay, positive terminal to the negative terminal. Whereas the electron flows in the opposite direction. The electron flows towards the positive terminal. So they are flowing in the opposite direction. So direction of current flow from positive terminal to the negative one. Okay, therefore current flows around a circuit in the direction of a positive charge would move. Electron moves in the other way. So electron moves in the other way, current is in the opposite direction of the electron. So very important concept. And the next learning outcome would be define electric current. So you should be able to define electric current and use electric current. Okay, so electric current is defined as the amount of charge that passes through, a wire's full cross section at any point per unit time. Okay, or it can also be the rate of charge flow through any cross section of a conductor. So we know charge is Q per unit time T. So our formula for average current would be Q over T. So amount of charge of current per unit time. So how much charge travels per unit time. For example, 5 seconds. So how many charge travel, or the amount of charge travel in that 5 seconds. So that would be your current. So for example, if there's 10 charge travel in that 5 seconds. So your current would be 10 divided by 5. So you will get 2. Okay, so amount of charge travel per unit time. This is for average current. For instantaneous current, it's the rate of charge flow in a semiconductor per unit time. So it's dq over dt. This is the instantaneous. So at a certain point. And we have another equation which is Q equals to NE. Okay, where Q is the charge, N is the number of electrons, and E is the electron charge. Okay, steady current. Okay, so what do we mean by steady current? Steady current is the magnitude of a current does not change with time. That means for the first 5 seconds, there were 10 current that passed through. In the next 5 seconds, there is still 10 charge that passed through. Okay, for the first 5 seconds, there is 10 charge that passed through. And the following 5 seconds, there's also 10 charge that pass through. So we can see there is no change with time. So that means it's constant, it's steady. The current is steady. Okay, and the unit for current is ampere. And 1 ampere equals to 1 coulomb per second, because the unit for charge is coulomb and time is second. So ampere, the unit for current is ampere. And the next very important concept, or the very important law, is Ohm's law. Okay, you should be able to state and use Ohm's law. Ohm's law states that a potential difference of V across a conductor is directly proportional to the current I through it if its physical conditions and temperature are constant. So that means current and potential difference are directly proportional. That means if the current increases, for sure the potential difference also increases. Okay, so we have V over I equals to constant. It's a constant. Now we get Ohm's law. This is the equation, very important equation for Ohm's law. V equals to IR. Okay, where V is the potential difference, I is the current, and R is the resistance. Okay, and R is the resistance. So when a bigger V is applied, okay, for example, we have a bigger V. So when we increase the potential difference, okay, automatically the current will also increase. It's directly proportional. Or when we decrease, it can also be the other way around. When we decrease the voltage, the current will also decrease. Okay, so it works both way around. Ohm's law can also be rearranged as resistance as the subject. So it can also be R equals to V over I. We can rearrange it. Okay, it's the same. So we just rearrange it, where we can say resistance is actually the ratio of potential difference over current. Okay. Okay, what is actually resistance? So resistance is actually a quantity that resists the current from passing through. Okay, it resists the current from passing through. One analogy that can be used is, for example, we have a cliff and we have a river flowing. Okay, a cliff and we have a river flowing. So if the cliff is more steep, the water would flow faster. Okay, the water current would be higher. So this is the cliff. Okay, and this is the water. And we have stones or obstacles in the river. Okay, so we have stones. So actually, if we could use the analogy of cliff, where cliff is actually the potential difference. Okay, that means when the cliff is more steep, the water would flow faster, or the water current would be higher. Okay, so the water current would be the current. Okay, so when the cliff is more steep, the water would flow faster or with a bigger water current. Therefore, also the current also would be higher. So when we increase the potential difference, the water current when we increase the potential difference, the current will also increase. These stones act as an obstacle. Okay, so if we have more stones, the water would actually, it will be more difficult for the water to flow. So these stones are actually the resistance. So this is just an analogy for how Ohm's law works. So we know if the voltage is increased or the cliff is more steep, okay, the water current will increase. Okay, so that means the current will also increase. So when we increase the voltage, the current will increase. And resistors are the stones, which are the problems which makes the current harder to flow. So if the resistance increase, the current will decrease. So this is one analogy that can be used. Okay, that's about Ohm's law. And then next we go into defining and use resistivity. Okay, so resistance is now we talk about resistance. Now we talk about resistivity. Okay, resistivity is a measure of a material's ability to oppose the flow of electric current. Okay, so it opposes the flow of electric current. The symbol used is rho. So it opposes the flow. So it resists the flow of electric current. It tries to stop the electric current. Okay, resistivity is defined as resistance of a sample of material of a cross-sectional area of length 1 meter. Cross-sectional area of 1 meter square and a length of 1 meter. So there's a formula. Okay, so the formula is rho equals to RA over L. So where rho is the resistivity, okay, R is the resistance, A is the cross-sectional area, and L is the length of the conductor. Okay, so this is the formula for resistivity. Rho equals to RA divided by L. And the unit for resistivity is ohm meter. Okay, it's ohm meter. Okay, and the value depends on the material. So it depends what type of material or what type of wire we are actually using. So for conductors, we know conductors can transfer current very well. Okay, conductors can transfer current very well. So we say conductors have smaller resistivity because it resists the current in a very small amount. Compared to insulators cannot transfer current well. So we say it have larger resistivity. More current is stopped or resist. Okay, so that's about conductors and insulators. Okay, next. Okay, so not all wires or not all materials actually obeys Ohm's law. Okay, so we know Ohm's law where we say V is directly proportional to I. Okay, V is directly proportional to I. Okay, so only ohmic conductors obey Ohm's law. Okay, we say the pure metal obey Ohm's law. Then we would get a graph which is directly proportional. Non-ohmic conductors do not obey Ohm's law. So when they do not obey Ohm's law, we don't get the velocity and the current to be directly proportional. So we get a different graph. So we call them non-ohmic conductors. So for us to identify if a conductor is ohmic or non-ohmic conductors, we can see the graph. Okay, if the graph shows that it's directly proportional, then we can call it as ohmic conductors. Whereas if a graph is not directly proportional, it is a non-ohmic conductor. So for it to be an ohmic conductor, the velocity and the current have to be directly proportional. Okay, so the next learning outcome, you should be able to explain. Okay, you should be able to explain the effect of temperature on electrical resistance of metal. Okay, so now we look at what are the factors. Okay, what are the factors that actually affect resistance? Okay, so we have the earlier formula. The earlier formula from the earlier slide is rho. Give me a minute. Is rho equals to RA over L. Okay, so this is the resistivity, R is the resistance, A is the area of cross section of the conductor, and L is the length. But now we want to look at the factors that affect the resistance. So when we rearrange the equation, we will actually get R equals to rho L over A. Okay, R equals to rho L over A. So we know the resistance are affected by the resistivity, the length, and the area. So we can say the resistance is affected by the nature of the material, which is the resistivity. Okay, whether the material has high resistivity or low resistivity, whether the material is actually a conductor or an insulator, that affects the resistance as well. So that, which is the rho. Okay, and next one, the size of the conductor or the length and the cross-sectional area. So from here, we know if the area is reduced and the length is increased, the resistance would increase. Okay, so the resistance and the cross-sectional area is inversely proportional, whereas the resistor and the length is directly proportional. So the size of the conductor, which is the length and the cross-sectional area, affects the resistance. Okay, and the last one, this one is not in the equation, but the temperature also affects the conductor. So how does the temperature affects the resistance of the conductor? Okay, how does the temperature affect? So it is said that when we increase the temperature, the resistance will also increase. Okay, this is because we know we have a wire. Okay, a wire, and we have electrons in it. Okay, we have electrons in it. So when we increase the temperature, okay, when the temperature is increased, the electrons or the ions vibrate with greater amplitude. So when the electrons are vibrating with greater amplitude, it is harder, more collision happens. Okay, more collision happens, and it's harder for the electron to move around. Okay, so it's like you moving around in a room which is very crowded. It's harder for you to move around because everyone is moving around. Everyone is the electrons are bouncing or moving around with greater amplitude. So when everyone is moving around and there's a large number of people in a room, it's higher for us to, it's more difficult, okay, or it's less likely for us to move across the room. So that's why it's the same with the electrons. So when the electrons are moving around and vibrating with greater amplitude, more collision happens. Okay, more collision happens and the electrons are slowed down. So when the electrons are slowed down, the current cannot flow well. Okay, therefore the resistance also increased. So when the current cannot flow well, we are resisting the current. So when we are resisting the current, the resistance also increase. Okay, and we are introduced with one formula which shows us the connection between resistance and time. Okay, the resistance of a metal can be represented by the equation below. So R is the resistance at the temperature T. Okay, it can be any temperature, and R0 is a resistance at temperature T0. For example, initially the temperature was only 20 degrees, and then the temperature increased to 40 degrees. So your T would be 40 degrees and your T0 would actually be 20 degrees. Okay, and then your alpha is the temperature coefficient of resistivity. Okay, so this is the equation, and then we can get the second equation. This is the second equation. If we just rearrange it from the first equation. So we have the first equation, which is R equals to R0 plus R0 alpha delta T. So we multiply the R0 in. Okay, so we get this, and then R minus R0. So we bring this R0 to the other side, equals to R0 alpha T. And we know R minus R0, that means the initial resistance, the final resistance minus the initial resistance. Okay, this is R is the final resistance minus the initial resistance. So this is actually the change in resistance. Okay, equals to R0 alpha T. That's how we get the second equation. Okay, and like I said, R minus R0 is actually the change in resistance. Okay, so this is the equation for the resistance represented by time. Okay, so this is how time influences the resistance. So we have R equals to R0 in the bracket 1 minus alpha delta T. There's a delta here, delta T. Okay, so delta T is actually the change in temperature, so it's T minus T0. So how much the temperature has changed. Okay, the change in temperature, T minus T0. Okay, so that's all for until 3.3. Next would be 3.4. Okay, so for the next subtopic is 3.4, which is electromotive force or EMF, internal resistance and potential difference. So first things first, what is electromotive force? Okay, electromotive force or EMF of a battery. So EMF of a battery is the work done per unit charge. Okay, work done per unit charge. So for example, if the battery is labeled as 1.5 voltage, volt is actually 1.5 joule of work being done per 1 coulomb. So it would be the same if it's 12 volt. Okay, if the battery is 12 volt, it is actually 12 joules of work being done per 1 coulomb. So it's 12 joules over 1 coulomb. So the electromotive force is produced. Okay, the electromotive force is also produced due to the change in energy, which is from chemical energy to electrical energy. So when there's a change in energy, it generates an EMF. So this change in energy from chemical energy to electrical energy generates an EMF. So the work done is the electrical energy supplied by the battery to bring a unit of charge from one terminal to another terminal. So we know if the electron moves from the negative terminal to the positive terminal, so actually is the work done, how much energy it needs to bring that one charge from the negative terminal to the positive terminal. Okay, and the unit is volt. So it's the same as it has the same unit as potential difference, which is watt. Okay, so it is the work done to bring a unit of charge of electron from one terminal to another terminal through any resistor. So if the circuit has a resistor, it would be a circuit too. Then we can calculate the EMF lah. So the work done to bring a unit of charge from one terminal to another through any resistor. Okay, and then we discuss about internal resistance of a battery. Okay, so actually, this resistor not only refers to the resistor in the circuit, but actually, even the battery has its own internal resistance. Okay, and as we know, resistance oppose the flow of current within the battery. Okay, it hinders the flow of current. So it opposes the flow of current within the battery. So for example, usually we will label it as negative terminal, positive terminal. So negative terminal, positive terminal, and then we have the resistor, and then we have the circuit. So all this would be actually the battery. So the battery itself has its own resistance, which is the internal resistance of the battery. And as other resistance, the unit for internal resistance is ohm. Okay, it will be ohm. So the next learning outcome is state the factors that influence internal resistance. Okay, so internal resistance of a cell is the resistance offered by its electrolytes to flow of the ion. So in the battery there's electrolytes, and these electrolytes resist the flow of the ions. Okay, so we know in the dry cell there's two terminals, the positive terminal and the negative terminal. The positive terminal is where the current flows out from, and the negative terminal is where the current flows in. Okay, the current flows from the positive terminal to the negative terminal, whereas electrons flows from the negative terminal to the positive terminal. In a dry cell, positive charged cations move from the negative terminal to the positive terminal. Okay, so there is four effects of internal resistance. The first one, internal resistance is directly proportional to the distance between the electrodes. Okay, so it's directly proportional. So if the distance between the electrodes increase, the internal resistance will increase. Okay, the internal resistance is also directly proportional to the concentration. Okay, so we know if it has higher concentration, it has less ions of electrolyte. Okay, so when the concentration increases, the internal resistance also increases because it's directly proportional. Okay, so when the distance increases, the internal resistance increases. Also, when the concentration increases, the internal resistance also increases. Next one, the internal is inversely proportional. Okay, the internal resistance is inversely proportional to facing surface areas of electrolyte. So if the surface area of the electrolyte increases, the internal resistance decreases, and is inversely proportional to the temperature of the electrolyte. So if the temperature increases, the internal resistance decreases. So these are the four factors that influence internal resistance. Okay, moving on to the next learning outcome, which is you should be able to use terminal voltage V equals to EMF minus IR. So I'll show you how we got the equation. Okay, so a device that supplies electrical energy. Okay, the device that supplies electrical energy, like I said earlier, when chemical energy is converted into electrical energy, it produces a source of EMF. Okay, and since the battery itself has its own internal resistance. Okay, therefore the terminal voltage is not necessarily equal to the EMF. Okay, so for example, the battery is labeled as 1.5 voltage. Okay, for example, the battery is labeled as 1.5 voltage. But when we put a voltmeter across it, we do not get the reading of 1.5. Maybe we will get a reading of 1.4 or even below. Okay, so the terminal voltage is from here to here. So for example, if we have a voltmeter here, the reading of the voltmeter is not necessarily it will be equal to 1.5 voltage, because it has a resistor here. So the reading here you would usually be smaller. So if, for example, if it's 1.4 voltage, and since it's parallel, since it's parallel here, so if I put another voltmeter here, here would also be 1.5 voltage. Okay, so this one, this and this is called as the terminal voltage, whereas 1.5 volt is called as the EMF. We call that the EMF. Okay, so not necessarily a battery label 1.5 voltage would actually have a terminal voltage of 1.5 voltage as well. It could be smaller, okay, due to the internal resistance of the battery itself. Next is the waterfall analogy. So it's the same. The EMF would represent the height of the waterfall. Okay, so the higher the waterfall, the more the potential energy it has. Okay, so when it has more potential energy, when it hits the ground, so when the waterfall is more steep or the waterfall is more higher, it will have a higher potential energy when it hits the ground, and the current represents how much water falls each second. Okay, so we know if it's higher, more water would flow, therefore more current would flow as well. Okay, and resistance refers to any obstacle that slows down the flow of the water. So for example, it could be the stones or a wood or anything that would actually slow down the resistor. Okay, so this is an analogy to represent EMF, current, and resistance. Okay. And next, so we know, okay, so this is what I said earlier. So this is the terminal voltage, and if we put a voltmeter across A and B, we will get the same terminal voltage. Okay, so for instance, the EMF could be 12 voltage. The EMF would be 12 volt, but it's not necessary that we would actually get a 12 volt of terminal voltage. This is due to the internal resistance, which is 2 ohm. Therefore, we could actually get this equation where EMF is equals to the terminal voltage, equals to the terminal voltage plus IR, where I is the current that passes through and the small r is internal resistance. Okay, so when we add up the voltage, the terminal voltage, and also IR, okay, I current and small r is the resistance, we will actually get the EMF. But since we know V is also equals to IR, okay, this capital R represents the external resistor, the small r represents the internal resistor. Okay, so when we replace V with IR, so we will get I capital R plus I small r. And we know, okay, since it's a series circuit, the current would be equal at any point. So we can factorize out the current and we will get EMF equals to I capital R plus small r. Okay, that's how we get the first equation. So this is actually the equation of internal EMF. Okay, this is actually the equation of EMF. Okay, we could also rearrange it. And this is one way of writing it. Another way of writing it is we could rearrange it. So V would actually equals to EMF minus with IR. This would also be another equation. Okay, so it's up to us. Let's see which equation we have, which data we have, and then we can choose our equation accordingly. But what I would like to highlight here is this represents the resistor of the circuit. Okay, so this is the resistor. We have the external resistor here, and this is the internal resistor. Okay, so the resistor acts as a tool which actually consumes the energy. So we know the battery actually produces or gives out the energy, whereas the resistor consumes the energy. So since there's internal resistor in the battery, some of the energy produced by the battery, the EMF produced by the battery is actually consumed by the internal resistor of the battery itself. Okay, so that's why the terminal voltage is not equal to the EMF. Okay, so this resistor actually dissipates or consumes the electrical energy, and then we assume the conducting wire has negligible resistance. So we assume the conducting wire does not have any resistance. So now we compare the difference between EMF and voltage. Okay, EMF is the amount of energy supplied by a source. Okay, EMF is always a source which produces the electrical energy. Okay, it can be from any energy, then it produces the electrical energy. So for this case, if we are using a battery, it will be from a chemical energy to electrical energy. So EMF is the energy supplied by the force to a unit charge. Okay, to a unit charge. Whereas voltage is the energy used or dissipated by a unit charge to move from one point to another. So that means voltage is how much of energy is actually used up. Okay, how much is energy is actually used up by a charge which moves from the negative terminal to the positive terminal. So how much of energy is used. So EMF and voltage is actually very different. And this is the formula for EMF. But else voltage has a formula V equals to IR. Even the symbols are different. And to measure, okay, to measure EMF, we will measure between the endpoint of the source when no current flows through it. Okay, that means we have a circuit. Okay, we have a circuit, but there's no current flowing through it. Then we can measure its EMF. Okay, because when there's a current flowing through it, it will automatically be affected by the internal resistance. Voltage, on the other hand, is a measure between any 2 points in the circuit. So it can be at any point of the circuit, we can measure the voltage. So this is an example. So for the EMF, we can only put a voltage across the cell without a current flowing through. Okay, and then we can calculate the EMF, or we call it open circuit. To calculate the voltage, we need to put a voltmeter across a cell which also has a resistor. So this lamp has its own resistor. So then we can calculate the voltage of the circuit. Okay. So this is the equation I said earlier. Okay, so the next learning outcome is describe the relationship between EMF of the battery and potential difference across the battery. Okay, so we have EMF equals to IR plus terminal voltage, and we can rearrange it as terminal voltage as the subject, and EMF and IR. Okay, and then here we have when the battery of an EMF is connected to external circuit with a resistance. So we know when we connect the circuit with a resistance, the EMF will always be bigger than the terminal voltage. Okay, the EMF will always be bigger than the terminal voltage. Okay, the terminal voltage could also be bigger than the EMF only when the battery of the EMF is being charged. Okay, only when the battery is being charged, then the terminal voltage can be bigger than the EMF. Okay, and the terminal voltage will equal to the EMF when there is no internal resistance. Okay, if the battery does not have any internal resistance, and then only the voltage can be equal to the EMF, and it has no internal resistance and it's connected to an external circuit with a resistance R. Okay, and then when we put a voltmeter across the terminal, then we will get a terminal voltage equal to the EMF only when there's no external resistance. Okay, and our final subtopic for this video is 3.5, where we should be able to derive and determine effective resistance. So how do we calculate a resistance in a circuit? Okay, how do we calculate the total resistance in a circuit? Okay, so we know if the circuits are connected in series, if the circuit is connected in series and the resistors are in series. Actually, in series, that means they are next to each other. Okay, so we know the current will flow out here, and it will flow through all the resistor and flow out here. So that means we can say that at any point, here, the current is actually the same. Okay, because there is no junction. The current did not face any junction where it needs to be separated. So at any point, the current is actually the same. Okay. the current is equal. So the current is equal at any point. The same current flows through each point because it's connected in series. The resistors are connected in series. However, the voltage across the terminal here would be equal to the voltage across all three resistors. So that's why we have terminal voltage equals to V1 plus V2 plus V3. And then we know V equals to IR. Okay, V equals to IR, so we can replace V1 with IR1, replace V2 with IR2, replace V3 with IR3. Okay, Vt we replace with IREQ. Okay, and then since all currents are the same, the current I can be cancelled. And finally, we are left with this equation where the equivalent or effective resistance for a series circuit can be added up equally. So R1 plus R2 plus R3. So this is how you calculate a resistance if in series. So if the resistance are in series, so for example, if this is 5, okay, so for example, this is 5 ohms, and we have 5 ohms here and another 5 ohm here. Okay, so for the equivalent resistance, we just add it all up. So REQ will actually be 15 ohms. Okay. So this is if the resistors are connected in series. However, if they are connected in parallel, okay, if they are connected in parallel, it would be a different case because now the current is flowing through here. Okay, the current is flowing through here, and the current has to be split. The current splits into 3. Okay, 1, 2, and 3. So when the current splits into 3, we cannot say that the current is same at all resistors. So the current is not the same. So the current will flow here, and then when you reach here, some current would go to the first junction, some to the second one, and then some to the third one. Okay, so the current is not the same. And then when it flows out here at this point, all 3 currents would be added up together. So that's why for the current, I equals to I1 plus I2 plus I3. Okay, and since they are connected in parallel, so voltage across all resistance are the same. So we know when it's connected in parallel, voltage across all resistance are the same. So V a terminal equals to V1 equals to V2 equals to V3. So when they're connected in parallel, all voltage are the same. So for this time, we will rearrange it as, since V equals to IR, so when we rearrange it, we will get I equals to V over R. So we replace I with V over R, I1 with V over R1, I2 with V over R2, I3 with V over R3. And since the voltage are equal, it can be cancelled off, and we would be left with the final equation where I over R equivalent or effective equals to 1 over R1 plus 1 over R2 plus 1 over R3. Okay, so for example, if it's 5 ohms, 5 ohms, and 5 ohms, to calculate the effective resistance, it would be 1 over 5 plus 1 over 5 plus 1 over 5. Okay, so this is how you calculate the resistance if it's in parallel. So it depends. So the effective resistance is depends on how we connect the resistor, if whether we connect it in parallel or we connect it in series. So it would be different accordingly. Okay, so that's all for this video. Thank you everyone.